In this video, we solve problem number 2 from quiz number 5 in the fall 2020 semester. This differential equation is a homogeneous linear ordinary differential equation with constant coefficients. So we've got a third order equation. Since the differential equation is this type of equation, we're going to let y equal e to the mx. Since it's a third order equation, we'll compute y prime, y double prime, and y triple prime. Derivative of e to some power is e to that power times the derivative of the inside. Derivative of the inside is just m, and we do that again. When we take the derivative of this, we get an extra m. So every time we take a derivative, we get another m due to the chain rule. And then we take these and we substitute into the differential equation, and then we simplify. So y triple prime is m cubed e to the mx. And we have minus 5 times y double prime, which is m squared e to the mx, plus 3 times y prime, which is m e to the mx. And then we're adding 9 times y, which is e to the mx. And we're setting that equal to 0. Now, if you factor out that e to the mx, you've got this. And e to the mx is never 0. So we end up with this third degree polynomial in m that must be satisfied in order for e to the mx to be a solution to the differential equation. So if we can find the values of m that satisfy this equation, we can find the corresponding solutions to this differential equation. Once I know m, I just plug it in here to find linearly independent solutions, again, depending on the values of m. Okay, so I need to solve this equation. If it factored easily, I would factor it, but it doesn't factor easily. I can't factor by grouping, so I'm going to have to try something else. What we learned in class was to use possible rational roots. So my polynomial equation is m cubed minus 5m squared plus 3m plus 9 equals 0. And the possible rational roots of this equation come from taking the factors of the constant term and dividing by the factors of the leading coefficient. The constant in this case is 9, the leading coefficient is 1, so we just want the factors of 9 divided by the factors of 1. Factors of 1 are plus and minus 1, factors of 9 are plus and minus 1, and plus and minus 9, and plus and minus 3. 1 times 9 works, negative 1 times negative 9 works, 3 times 3 works, and negative 3 times negative 3 works. Then you can take each of those and divide by plus or minus 1, but that doesn't really change anything. So we end up with a list of 6 possible rational roots, 1, 3, and 9, and negative 1, negative 3, and negative 9. So the question becomes, which of these values of m satisfies this equation? Now this method works for polynomial equations. So these are the possible rational roots of a polynomial equation. Okay, in order to figure out what will work, we'll just plug in values of m over here. It looks like if I plug in m equals 1, I'll have 4, and minus 5 plus 9 is going to be another 4. I'll get 8. I won't get 0, but I think maybe negative 1 will work. So let's try m equals negative 1. If it fails, then we can always try a different one. So I've got negative 1, I'm cubing it. I'm subtracting 5 times negative 1 squared. I'm adding 3 times negative 1, and then I'm adding 9. So I have negative 1 here. Negative 1 squared is 1. And then I get that. Negative 6 minus 3 is negative 9, plus 9 is 0. Great. And if you're wondering, how did I know that m equals -1 would work? Well, I was never sure until I actually worked this out. But my intuition told me -1 might work because when I plugged in +1, I had a 4 here, and then the -5 and the 9 were also 4. And I thought, maybe if I flip those signs on half of them, half of the terms, I'd have a +4 and a -4, and everything would cancel out. Um, yeah, and it turned out that's exactly what happened here. So we know that m equals -1 is a root of the polynomial. And if m equals -1 is a root, that means that m plus 1 is a factor of that polynomial. So we can write this third degree polynomial as this times some quadratic polynomial. And this quadratic polynomial is the quotient of this with this. Now it is just a coincidence that was Q. It was not Q for quadratic. It's actually Q for quotient. Okay, so we've got this here. In order to do this division, you can either use long division or you can use synthetic division. I would recommend using synthetic division. In order to use synthetic division, you take that divisor and you set it equal to 0 and solve for m. Or in other words, you find the root that is associated with that factor. We know the root is -1. You put the root in a little box over here. And then you list the coefficients of this polynomial in the numerator, and you need to include all powers of m starting with the highest power of m. And we're fine here. We already have an m cubed term, an m squared term, an m to the first term, and the constant, which is an m to the 0 term. So we're good. So we can just list those coefficients right there. We bring the 1 down, and then we multiply, and then we add. Multiply and add, multiply and add, and we get a 0, which is good because m equals -1 was supposed to be a root. If m equals -1 is a root, the remainder should be 0, and it is. So this cubic polynomial divided by this linear polynomial will be a quadratic polynomial, and these are the coefficients of that quadratic polynomial. So we've got 1m squared minus 6m plus 9. So the 1, the -6, and the 9 are the coefficients of m squared, m to the first, and m to the 0 power there. So this cubic polynomial can be written as this times that. And m squared minus 6m plus 9 factors to m minus 3 times m minus 3. So this one also happens to have a repeated real root. Now we wanted that set equal to 0, and we were solving for m. So we are writing the characteristic equation in factored form here. And then we've got this, and we say, well, from that we can find the values of m. Now it was a third degree polynomial, so there are 3 values, m sub 1, m sub 2, and m sub 3. So m sub 1 comes from setting that first factor equal to 0. That's going to equal 0 when m equals -1. This one equals 0 when m equals 3. And so we'll have 2 different values of m that correspond to that factor because that factor is repeated twice. So we get 2 m values. Well, then the corresponding y values are y equals e to the mx. So y1 is e to the m1x. And over here, y2 is e to the m2x. But y3 can't be e to the m3x because m2 and m3 are the same thing, and y sub 3 has to be linearly independent from y sub 2. We said before, though, that if you have a repeated root like this, it turns out that multiplying by x works. And if you're saying to yourself, where does that come from? We mentioned that you can use reduction of order to get that x value, that if y2 is a solution, what would be another linearly independent solution? X times this function ends up being the second linearly independent solution if this m value is a repeated root. Okay, so we've got our y1, y2, and y3. And that's enough to state the general solution. The general solution of the differential equation comes from taking those functions in the fundamental set of solutions, or a fundamental set of solutions, multiplying them by constants and adding them together. So you have c1y1 plus c2y2 plus c3y3. So that's c1 times e to the negative x plus c2 times e to the 3x plus c3 times x e to the 3x. And this will work for all real numbers x. And that's our general solution.